Good evening, everyone, and welcome to the Baumer series. My name is Eric Herman. I'm an assistant professor of architecture here at the Knowlton School, and tonight it's my privilege to introduce the speaker, Paul Lewis. Paul, alongside Mark Shuromaki and David Lewis, is founding principal of Lewis Shuromaki Lewis, or LTL Architects, an internationally recognized practice whose accolades and recognitions are both impressive and numerous. I'll simply note here that the firm was featured at the U.S. Pavilion at the Venice Architecture Biennale, and its work is in the permanent collection of the Museum of Modern Art, the San Francisco Museum of Modern Art, and the Carnegie Museum of Art. Paul is a professor at the Princeton University School of Architecture, teaching there since 2000, and a past president of the Architectural League of New York and a fellow of the American Academy in Rome. So tonight's talk inaugurates an exciting part of the school's public programming, the opening of LTL's exhibition in the Banvard Gallery, Bionic House Sections. So I want to acknowledge and thank my colleague Sanjay Kochar, who's the Banvard Gallery chair, for helping to organize the show. And the exhibit comprises 3 parts: an exhibition of a new book, a selection of building materials, and 5 small houses designed by the practice. For those on your first visit to the school, congratulations on finding the auditorium. The gallery is located that way, under the big steps, and just follow the crowd. So founded in 1997, the work of LTL embraces an architectural design approach that favors tactics over strategies. Equally grounded in practical and speculative acts of imagination, the firm's work reveals the inherent messiness of the everyday, the routine, and the conventional by transgressing, reframing, and reinventing. In projects that range in scale from small gallery interventions to enormous amphibious landscapes, LTL, often in their own words, rejects the boundaries of acceptable practice. It could be the early clothing store projects or the enduring image of Paul ironing enormous canvases of drawings for their Venice Biennale installation, but somehow I've always associated their work with the notion of tailoring, and I'll offer 2 reasons for that. First, a good tailor is highly observant to both nuances of posture and anatomy, things that other people might miss. And at moments when a debate might arise around the relative importance of a building's posture or its form and its anatomy, its systems, LTL's body of work forcefully replies, it's both. The practice intertwines these dual concerns and the nuance of their observations through the use of the sectional perspective, the forceful drawing type that has been central representational conceit for the practice since its inception. It's often copied, never quite duplicated, and every architecture office has its own standards and styles, but it's exceedingly rare to own a form of representation to the point of making it categorical or definitive. The space between drawings and construction is fluid in LTL's work, with stunning drawings of intense activity and representational tropes like clipping planes, anamorphic projection, and section cuts materialized and spatialized in the built form. The second reason I understand them as tailors is that Paul and his colleagues at LTL make and alter equally. They don't just design, they augment, mend, and tailor spaces to novel uses and means. They do this literally, such in the case of renovating or expanding an existing art museum, but also conceptually, weaving together typologies of towers and parking garages. In each case, they enhance and alter found materials, types, or conditions to suit entirely new uses with incisive acts of architectural imagination. So as I turn the podium over to Paul, I'll note that LTL's focus on embodied energy and building systems continues its restless search for imaginative alternatives. After all, you're never really short of inspiration if you focus on how messy even the simplest things can seem. In the most recent body of work on building with biomaterials through parallel bodies of research and design, which Paul will share tonight, they continue to ask forcefully the practice's foundational question, what if? Please welcome Paul Lewis.
Thank you, Eric. That was really good. That was really good. Perfect. So thank you. Look, it's a real pleasure to be here. I'm originally from Ohio, so to return here is like returning home, and in some respects, this is a kind of return to an exhibition that we had done here in 2016, where when we first exhibited the manual section. And not only was this the opportunity to exhibit the work, and the armatures that were used for the exhibition related to this book are being reused again in this exhibition. But this was also the first time I'd ever lectured on the manual section. I was terrified, and there were some questions about, oh, can you really design in section? And I was like, yeah, no, you can. This is where, and in fact, we're going to make it legible. This book has had success beyond what we expected. It's been translated into at least 7 languages. We're still looking for the Turkish edition. If anyone sees it, please send me a copy, or at least a photograph of a copy. But it's been rewarding in a sense that doing something has had a bit of traction. But I will say that the book I'll present tonight, in some respects, we feel is actually more important. It may be less canonical, but in some ways it's actually making it more the crisis of climate. In a sense, imagining a new paradigm, if you will, for architecture based on completely changing the assumptions about what materials we should be and can build from. So the book is based on 9 different chapters, with a 10th chapter on reuse. And reuse for us has been the basis of a lot of our work. We really enjoy working with existing buildings. The idea of layering history, tailoring, I think, is a great description for it. Modifying things, looking at the accrual of time through the kind of alterations that occur within a building and become manifested as layers within a building. But you also get the opportunity of taking existing buildings and strange qualities of those buildings and being able to make spaces that you would otherwise not be able to do if you're going to do it ground up based on convention. So here, an office space for 100 employees, column-free space because it used to be a maintenance building. So interesting kind of frictions between past and present, reworking piers, and here, this is a pier in Coney Island where the structure was still intact and we could redo the surface, redo the benches because it had been damaged. Or here, kind of an interesting friction between a very contemporary coffered ceiling that got stretched and pushed and pulled in different ways, mostly to open up the windows of the McKim and White building on Columbia's campus. So this design process of working with reuse is often a kind of question of kind of thinking about what are the constraints that one has to put into a building and how can it set up these intriguing kind of frictions with what's already there. So this is a museum for posters. It's a super long site, 220 feet long, goes through an entire block in New York. But we had to find a way to make a humidity-controlled gallery space within this building, but to try to take advantage of that incredibly elongated space. And so that went through a series of iterations and kind of volume nested logics in terms of section, thinking about ways to torque this so that maybe through elongations of lines, we could actually get a kind of knot at the gallery entry, and in a sense producing a long street, which is of course the right location for a poster anyways. It meant weird qualities. Basically we made a 220-foot long piece of millwork that had to step down the site because of course 24th Street and 23rd Street were not at the same level. They were off by about 3 feet. So the entire space inside slopes. So that became one component, and here you get a sense of the street or the alleyway within the heart of this building. And a lot of the work here is played out through materials, finding ways to take the materials away to register the difference between the old and the new, the nested space within it, the role of the white oak to be able to manifest the inhabitable piece of furniture down the length of the building, the conventional gallery, but also the kind of unique features that would be highlighted within this space. And we really liked, again, the ability to look at new construction here. This is a clay-based kind of wall surface that would then be used to frame and encapsulate and even highlight some of the existing cast iron columns. But a lot of the reuse for us historically within the office has been really focused on operational carbon. A lot of the geometries, and this is not untypical for architecture. We're trying to deal with the questions of the built environment's relationship to climate through operational carbon. So you end up deforming window shades. There becomes lots of torquing to facades, et cetera. But there's a limited agency you have. A lot of the work is mechanical systems. A lot of the questions about energy are not ones that are played out within the realm of what the architect directly deals with. Now, the interesting thing is that the embodied carbon question, the material carbon, changes that. And that's super interesting. So most of what I want to present today is really a kind of combination of these two things, the manual biogenic house sections, and then a series of designs that we did in parallel to that book. Let me set the stage. And this, for some of you, are like, oh, please don't say this again. We know this, we've heard this. But for those of you who've not been witness to this, and again, this is not our argument. This is an argument that others have made. But we know that greenhouse gas emissions are way too high with potentially catastrophic effects. We witness this all the time. Current policies are not sufficient, as we know. And the target, in a sense, if we're going to be able to get to net zero by 2050, it means significant reduction in the next 7 years, which is increasingly dire. And again, this issue that operational carbon is a big component of the built environment's carbon emissions, but the embodied carbon has been understudied, not been influential yet. But the whole package of the building industry has a huge chunk, is a huge chunk of global carbon emissions. So 39%, et cetera. The interesting thing is that if you look at new construction and you map it out between now and 2050, the embodied carbon, or the carbon used to make the building, is going to really account for 50% of that carbon, in part because the operational efficiencies have improved. This becomes even worse with high performance buildings because you're increasing the thickness of the insulation. You're using a lot more kind of basically higher embodied materials. So you get a much higher percentage of embodied carbon in the high performing building. And worse yet, it's played out over a number of years, right? So you've already bought that carbon up front through the materials, and the operational is only going to see the benefit over 25, 30 years. So in a sense, this is really changing how we have to think about building materials. And some argument is that, oh, we should just reuse everything, which is great, but it's not going to account for the demand, the global demand for buildings, which, some estimates have, trillions of feet, 2.5 trillion square feet of demand for building by 2060. So we can't reuse our way through the rest of the future, even though one has to reuse continuously as much as possible. Well, what this does is make an argument, and I think this is really compelling, which is that we need to change the material basis of design. Most of the 20th century and most of modernism has been defined by petroleum-based materials, steel, glass, concrete, and we have an opportunity now to imagine a kind of very different 21st century where working with plant-based or biogenic materials, geogenic materials, we can look at materials that are regenerative, that are largely acquired locally. They don't have toxicity beyond, I should say they don't have the toxicity at the sites that the petrochemical materials do. So there's a whole series of benefits that come from this. Most importantly, it puts the agency into the realm of architects, right? So you're not saying that it's going to be the mechanical engineer who's going to be doing this. It's at the level of the materialization of the building. The problem is we need to figure out how to do that. And that many of these materials just don't exist. They're not at a level of development. So there's an interesting question of how do we start to look at this future when we don't have as many great examples and as many great materials to work from. So that was really the basis of our book. We know that materials are not equal in terms of their carbon impact. Glass, steel, and concrete are at the very high end, kind of off the charts in terms of their kilograms of CO2 emitted per meter cubed or meter squared. Whereas, of course, the ones that are all sequestering are ones that are plant-based, right? It makes sense. So the book that we developed is really trying to find a way to put forward a series of case studies, built case studies, that will make evident the possibility of constructing with plant-based or biogenic materials and finding a way that those had innovative architectural consequences. One of the key questions that we get and was a source of anxiety when we did this book is like, why houses? Aren't houses bad? Like, should we be doing more houses? And I completely agree. The problem is that in order to make evident examples that are built, houses are in some ways the best testing ground. They're the early testing ground for materials. They're the ways, in order to be able to draw buildings that existed, that were built, the house was the best typology to work with. The other advantage is that relative to drawings that fit in a book is that with a house, it would be small enough that the cross-sectional perspective would actually show you the tectonics. Whereas, I don't know if you know a manual section, if you look at some of those big buildings, you can't tell what's in the, we don't know what's in the wall, you know, it wasn't relevant for the drawing. So, but here we can draw them, we can show the impacts of the tectonics because the drawing is legible at the scale. The other thing is that houses are not going to go away, but houses could get a lot smaller. So one of our interests is only showing houses that are about less than 1,000 square feet. Almost all of the houses in the book are on the small side. So in a sense, the book is kind of a critique, if you will, of the single family house. This kind of known I guess typology has a lot of problems. And I won't go into all of them, but one key one is that where the average single family house was about 1,000 square feet in 1950, I should say, it's grown 2.5 times by 2020. So it's much larger than it needs to be. Its carbon footprint is quite significant. And more importantly, it's almost all, the entire thing is constructed out of a high percentage of plastic, petroleum-based, chemically loaded, relatively cheap materials, which end up not only having kind of toxic effects on where they've been extracted, but also their end of life. The make, take, and then dump. These materials don't have the ability to decompose. They can only wear out and end up in the landfill. So the other thing from a standpoint of design that we became really interested in is the problem of the wall itself. And one of the difficulties of contemporary construction is that if you look at the sandwich of the wall, it's made up of an incredible number of very small, thin, single performing layers that they're lightweight. They're multiple. They often only do one thing and are legally accountable for that one thing. They're hygienic, meaning they tend to argue for their cleanliness and their maintenance-free qualities. And they produce a strict binary between interior and exterior, which Fu, of course, is going to argue against. Like, we do not want strict binaries between interior and exterior. We want to embrace a much broader expanse. But this is one of the problems. And the other problem with architects is we tend to only obsess about the paint surface and the exterior surface, and the thickness is not something that we deal with, and that's unfortunate. So with the book, we became much more interested in kind of thicker walls, monomaterials, things that did had multiple performances, and this is often where plant and earthen materials operate. It's a super interesting way of thinking it, but it pushes up against conventional construction. It pushes up against the trades. There's a lot of problems that have to be overcome, but it's something we find super interesting. So the book spent a lot of time, to make the book, you spent a lot of time looking at the cross sections, looking at the materials, trying to understand how these things were put together. So let me go through these a little bit more slowly. I should say that the book, each of the chapters of the book set out the relative carbon kind of footprint, the approximate carbon emissions, the sequestering per meter cubed of each of these materials. But we introduce each chapter with, in a sense, an overview of the material path from plant to construction and how its reuse or end of life is enabled by these more circular systems. We looked at the kind of overview of the kind of specific process of each of these materials from that kind of plant life. How long does it take to grow? How is it harvested? And how does it work its way into a specific building material? And what's available now on the market? And what are the forms? And that's not to say this is the only version, but right now these are the dominant models. We then drew axonometrics, exploded axonometrics to understand how the house worked, but also wanted to show the house under construction and interior and exterior photographs to see what the effects, the kind of consequences of these materials were. There were about 6 to 7 houses per material in the book, and then they would each culminate in a cross-sectional perspective that Eric mentioned earlier, which we like because it's this weird combination of a highly abstract drawing, it's a measurable section, combined with a kind of subjective, inhabitable perspective. So you get these kind of two very different kind of drawing types superimposed together. They're also just like enjoyable to look at the level of detail and to see the consequences on the perspective of the kind of tectonics. We worked about 4 years on this book, and at the end of those 4 years, we were a little frustrated because we didn't get to do any of the design, so we actually designed 5 houses based on what we thought were the interesting possibilities that these materials presented. So I'll kind of present both of these things together. We usually looked at multiple materials within each of these houses, so it's never just one material that is interesting. It's the hybridization where there's a lot of potential future moving forward. So mass timber, like you all know mass timber, right? It's become a kind of ubiquitous replacement for concrete. It's the poster child for plant-based materials. Carbon-wise, it's certainly better than concrete, but it has some important limits. It's not going to save us, and it's a more evolved building product in the plant world than most others. The manufacturers' codes, contractors are somewhat on board. They're mostly embracing it, and so it presents a path for other plant-based materials. But the limits are pretty clear, which is it takes a while for a tree to grow, right? 30 to 100 years, and even with Forest Stewardship Council managed forests, the carbon loss from removing the tree and disrupting the soil significantly offsets whatever carbon sequestering you're going to get from the mass timber. And typically, only about 50% of the tree is used in the production of CLT. And so it's essentially a net zero benefit, if you will, at best. So that's not exactly the perfect way to move forward, but it has impressive structural capacity and certainly is something that we have to kind of work with as much as possible. The downside is I've been on a lot of studio reviews where the Rhino model used to translate into concrete, and now it translates into CLT without any understanding of what that means. So just be careful of CLT is not just a new version of concrete. It has different qualities. And the other problem is that CLT is largely a product of glues. So, and there are interesting ways to replace the glues with, say, dowel laminated systems, which are well worth looking at. The interesting thing is to find ways that the CLT can have spatial and architectural and formal consequences. So a really good example is Jennifer Bonner's house Gables, which is really only possible to be produced by using multiple CLT pieces, custom cut. Even though the gable is often a product of stick framing, here the complex geometries of all of these gables really only possible with the structural and tectonic capacity of CLT. Or another example, Atelier Sotoma's meteorite. Here, this is a really weird house, by the way. There are 2 layers of CLT that are nested into each other, basically a volume inside of a volume. Not only produces this enigmatic figure on the landscape, but the argument is that the space between these 2 layers is essentially an insulative cavity, despite the fact that nothing is filled into that space. So it's an interesting argument. So you end up with a house that's basically made out of CLT with only a kind of blackened stain on the outside, and that's it. So two simple materials and using the space possible through the CLT construction to get to this end. And it happens to sequester 48,000 kilograms of CO2 equivalent. All right, so with the A-frame house, we were interested in not actually milling a CLT blank, but using the entire blank. So rather than go through the process of kind of cutting it into small pieces, what happens when we use the entire piece of CLT? So this house is made up of 5 pairs of 10 feet wide by 50 foot long CLT panels that are placed up against each other. A stair at the back is used to structurally stiffen the back group, as well as provide the circulation up through the A-frame. Whereas as you move to the front, it forms the iconic A-frame, except this one's really tall. It's almost 50 feet tall, right? So you end up with the stair at the back accessing the roof deck, and that roof deck cascades up to provide a kind of lookout across the Pacific. I think the site was sited in the Pacific Northwest. Whereas on the inside, that super high space was then inhabited by stretching the staircase into the space. And of course, with CLT, you don't have to necessarily apply all the interior finishes of gypsum, latex paint, et cetera. You can just basically work with the CLT itself. But we like the kind of unusual proportions that were made possible by this fantastic plank, which is rarely used as a vertical surface in this way. So bamboo, the other structural, kind of major structural plant-based material, grows a lot faster than wood does, and as a result is in need of further advancement and development. Its growth is prolific. It has a higher rate of carbon sequestering than wood. It's not clear cut. It tends to be individual culms of bamboo are harvested independently about every 3 to 5 years. It can grow 30 feet in that time. And has kind of great potential. It tends to be like CLT, cut into smaller strips and then glued together. So the question of the adhesives is really key. But it also can be used as culms, despite their natural variation, providing a kind of an intriguing structure based on bundling. So just one house that does that, house in Ecuador, clusters these kind of large indigenous culms into a structural frame. Basically organizing and intersecting ramps. So with all these houses, we had to like the section, right? And so this one, the idea that you'd have this continuous ramp that would bring you up and through the house, but also provide the diagonal bracing. So lateral bracing being provided by the floor, which we find kind of fascinating. Another project, Anna Herringer's housing prototype, really developed a kind of weave of bamboo forms using the kind of unique qualities of bamboo to form this semi-protective skin. And then inside of it, a rammed earth interior sleeping core was positioned. And really, the skin was only possible through the unique kind of flexibility and lightweight quality of bamboo. So earth, which was part of the, Anna Herringer's work here, earth is worth looking at. So even though we called the book Biogenic, and we had a lot of anxiety about the fact that earth is not biogenic, but we couldn't say, we didn't want to have the manual of biogenic and geogenic, how it just was, it was getting too unwieldy, so we stopped at biogenic. But, so earth is not great in tension, but it's actually quite good in compression. So it can be a load-bearing structure. It's one of the oldest building materials. It can be inexpensive, although the labor brings up the cost. It's inherently local, and its thickness works as a thermal mass and also can absorb and balance humidity. And if clay is used as a binder, its carbon emissions can actually be quite low. The problem is most rammed earth that we see in the world, in the construction world, has very high levels of Portland cement. It's basically a version of concrete. So it's better to use lime or just clay as the binder. But because it moves from a liquid to a solid state, it can be used to form blocks and other kind of prefabricated elements. So in the Von Haus Fleury, what we really liked about this house is that the walls are 32 inches thick, combination of straw and earth, and they're just cut with a spade. I don't know if you can see in the construction site on the lower right. It's stacked up and then sliced manually with just the spade. So that you get these kind of contrasts between the crisp geometry of the light wood floor and these rougher walls. And there's something about moving past these super hygienic interior spaces that we associate with, proper living, that somehow this actually introduces a very different aesthetic, which we find very, very appealing. So the floor and the wall were filled with straw as well, with large overhangs to help protect the earthen wall from erosion. And in a sense, this is basically a insulation, cladding, and interior finish all combined into one. And the structure is really carried by the stud walls that are buried within the inside of the earthen walls. Really interesting house. A different earth-based project using more kind of prefabricated bricks. This uses 15,000 loam bricks, 4 by 8 by 16, by LTL Architecture in Burkina Faso, where the walls and the vaulted ceiling were all assembled locally from these bricks. There was a very thin corrugated roof placed over top of the bricks to protect them with a thin metal truss. And this not only provided that protection, but also harvested rainwater down the channels in the side of the building. So the other cliche that's spread across architecture schools is obsession with 3D printing, which I think is fine. So the problem is that most 3D printed architecture is done with Portland cement. Again, it's high, a lot of carbon footprint, despite claims that somehow it's better, which I think it is, but it's still it's a cement-based product. But there is a 3D printing company outside of Bologna, WASP, that's made a series of house prototypes just printing with local earth, which is really interesting. And Ronald Real is also doing amazing work in earth. Please look at his work with printed earth, but not printed concrete. And it's important to make that distinction. So this is, a half-inch layer developed over 200 hours, basically printing this wall system. It's a 30-inch thick wall, but most of it is hollow and filled in with rice husk for insulation. So for a design for what we call the lamella earth house, we were interested in how we could kind of combine the efficiency and strength of bamboo. Bamboo columns, not fabricated members, but the actual columns, with the installation of thatch and also trying to embed inside a larger building a kind of an interior living quarter made from earth extracted from the site. So the lamella structure, if you don't know a lamella structure, it's basically a kind of weave of self-similar members. These are all 8-foot, same joint. It just happens to kind of aggregate up. So 8-foot long bamboo parts, small bamboo parts, forming this kind of this shell, kind of half shell structure, and being able to kind of span a very large space relatively inexpensively. Thatch insulates the north side with operable translucent plant-based polycarbonate on the south, producing a kind of thermal gain. Really, this is seen as a passively conditioned interstitial space, and in a sense, lodged into that space, nested into that space, is the earth and living quarters that is half submerged into the ground. So you get a 300 by 292 foot long barn-like space, part greenhouse, but really something that introduces this interstitial in between an interior and exterior, and really trying to develop a different model for a working farmhouse within an agricultural landscape. All right. So the last three materials that I'll present are all insulation, or primarily used as insulation, which is probably one of the more overlooked aspects of a building. Few architects, including ourselves, ever really cared that much about insulation, as long as you got the R value up there. And the problem is that most insulation that's used in the world right now, particularly, well, certainly in the States, is petroleum-based. It's extraordinarily flammable. If you ever want to have some fun, take a match to a sheet of XPS and just watch it go up. So it's and there's all kinds of toxicity with the production of a lot of insulation, and it's a huge site for carbon emissions. So these three materials are offering an option that looks at insulation, and one of the questions is how far could they move within the architectural realm? Can this insulation material start to have consequences beyond being embedded within the wall? So hemp it grows incredibly fast, about 1 foot per week. It reaches maturity in about 3 months, so you can actually do 2 cycles of hemp growing within a single year a growing cycle. Its long root system does help regenerate the soil. It doesn't need much water, doesn't need fertilizer, doesn't need the pesticides. It's an incredibly hardy plant. The problem is that industrial hemp is fundamentally different than the hemp that you know of that produces THC, the psychoactive drug. And it's the association between those two, which is why hemp was basically banned for most of the 20th century in this country. And it's only within the past couple of years with a new farm bill that hemp was even legal to grow within this country. It has a fibrous stalk, which is used for paper, textiles. There's at one point a fantastic history of hemp production within this country. But the hurd has to be separated by an expensive decorticator. And then the material itself can be combined often with lime. So it's really a hemp lime system. It unfortunately is referred to occasionally as hempcrete, which is a bit of an incorrect kind of association because it's not concrete, it's not load bearing as a material, but it is fire resistant, rot resistant, humidity absorbing, it's acoustically beneficial, and it's good, it's obviously good insulation, but it's not a replacement for concrete. It can be sprayed, it can be formed on site, it can be formed off site in prefabricated panels, et cetera. So, and there's people doing fantastic work with hemp, and I think one of the interesting things is to see how these approaches to using these materials continue to evolve. The other, I wish the world was made with cork. We'd be a lot happier with like problems, it would solve a lot of problems. Cork is fantastic. It's a truly multi-purpose material. I can sing the praises of cork endlessly. Problem is it's just not available everywhere, and as a result, it's expensive, and it takes a long time to grow. So it's harvested every 9 to 14 years from the bark of a cork oak tree. It's water resistant, thermal. It actually can be structural, antifungal, acoustic, sensory. If you like the smell of cork, you're in heaven in a cork building. Some people don't, but they're wrong. So cork is just fantastic. So, but it's mostly concentrated on the Iberian Peninsula. And the cork used in building products is a residue of the wine stopper industry. So that tells you the kind of limit of cork as a building material. But there's some fantastic examples of houses. This is an experimental house where almost everything was constructed out of solid cork, a monolithic material that's truly structure and the interior finish and exterior finish. 1,268 custom CNC milled cork blocks that then were corbelled up to produce the roof, but basically making a single space. Again, it's fantastic material, but just limited in terms of its availability. It can't scale. That's basically the problem. On the other hand, the material I'm going to talk the rest of the lecture about can scale, which is straw. So it's everywhere. It's ubiquitous around the world. This is the fibrous stalk below the cereal grains of wheat, of rice, et cetera. It is ubiquitous. It's a waste product. It sequesters a huge amount of carbon every year that then is left either to be burned or to decompose and return the carbon back to the atmosphere. So the question is, how can we use this material and, in a sense, stall the decomposition process long enough and perpetually enough that we can, we don't need carbon sequestering or carbon extraction technologies because straw is already doing it at a massive level. So it grows, as you can imagine, super fast. It's cheap because it's agricultural waste. It's resistant to rot, and it can be used as insulation because it has a fair amount of air within the cell structure. And it can be used as a load-bearing structure. So that's the interesting question. How do you, how many other load-bearing installations do you know of? Like, there just isn't. Right? Cork, right? But that's it. And we know cork can't scale. So, right, typically straw is translated into a building material based on two processes. One is the role of the baler, which provides a kind of pre-compressed, readily available product, if you will, but it's not the right product. It's what's out there now, but it's not a great building product, and it tends to have to then be surfaced with the second component, which is a fairly thick plaster skin. That provides the protection from the rain, it provides the protection against insects, fire, and it increases the structural capacity of straw. And typically straw is used as an infill system. It's not usually used structurally, although the Nebraska load-bearing structures are examples that have been around for over 100 years. Fascinating, but again, it's the plaster that's applied on top of them that's key, and that plaster is not cheap. It's fairly labor intensive. It can be used as a wood frame infill, as you see in the middle example, or it could be used as a prefabricated panel, whether it's a double structure stud system, or in this case, a kind of box cassette, plywood or CLT. Thatch is a different version of straw. It's a slightly different reed, harvested it into bundles to make roofing. That's its own kind of fascinating world, which I won't go into much. There are some really interesting examples that are worth looking at more closely relative to straw. So this is Atelier Schmidt's Gardas Pavilion, which uses jumbo bales. And these are really big bales, 30 inches, 50 inches, 100 inches, 650 pounds each, and used as a load-bearing wall and a corbelled ceiling. So you effectively get this super thick, insulative, structural blanket containing 75 metric tons of agricultural waste, or put another way, it's about 84,000 kilograms of CO2 in that small pavilion. So we were interested in this idea of thickness. So with straw being readily available, cheap, there's a possibility not of assuming that the modernist obsession with thinness is the necessary trajectory. Well, what happens if we actually use thickness as a catalyst for domestic space that could be fundamentally different? So the next two houses we designed that I'll present are really looking at how straw bale and their associated thickness could be a different model for developing a domestic space. So with the, that was my voice cracking. So with straw bale, the project called the Straw Bale Spiral House, we combined two different materials. We looked at how CLT could be used to make, in a sense, solid frames that would carve voids within the mass of a kind of thickness of straw. So in a sense, the project really starts out with a stacking of a series of a block of straw. I think these are about 4 to 6 straw bales in each direction, and then stacked up about 12 high. And the CLT prefabricated units or rooms are then carved out from within these. So in a sense, the CLT stabilizes the bales and then forms the interior of the house as a form of void within the straw. A CLT stress-skin roof cantilevers on all sides, in a sense protecting the straw's clay plaster. And then a central skylight is able to bring light down to the interior of the central void. So what you get really is a spiral of CLT boxes that form, in a sense, the primary program of the house. And these move from the front door all the way up through the different rooms within the house up to a roof terrace. So it's really a kind of CLT way of skinning the interior of the straw, which then insulates and supports the CLT. So putting these two materials into kind of dialogue with each other. We also like the idea that the CLT rooms are also windows, are a kind of void that only exists by the removal of the straw that is otherwise kind of existing around the thickness of the space. So with the second house, the mass straw house, we wanted to find a way that we could look at two different ways to approach the jumbo bale. So one of these deployment of straw was aligned with the slope of the site, kind of perpendicular to the slope of the site. And the other was a stack of straw bales that forms a terrace step moving in the other direction up the site. And these two were then connected together with timber box beams that anchored these two kind of straw assemblies or thicknesses to each other. The roof is clad in plaster, in clay plaster, and a layer of hemp fiberboard. An additional layer of unprotected straw is then added on top and left to decompose as a kind of green roof. We kind of like the idea that everyone says, oh, you're working with straw, are animals going to eat that? First, straw isn't hay. Hay is vegetables. Hay is what animals eat. Animals don't eat straw, but we like the idea that, okay, we'll make the roof of the building edible. If people want to let the animals eat it, fine, they can burrow in it. It's excess. It's a kind of an excess thickness. And it also allows the building to kind of blend into the site, which we found very appealing. But more importantly, on the inside, the main space of the house is really the space between these two thicknesses. And then the bedrooms, the private spaces, are really carved out of the excess of thickness of the straw bale kind of zone to the right in this image. So you have incredibly private rooms, acoustically private. They all lead to skylights, but you get this collective space for the gathering of everyone together, but you can then move back into your private bedroom with your view to the skylight. Incredibly quiet, if you can imagine. This is clearly coming from a bunch of urban dwellers who want to get into a place that has no noise whatsoever. But we really like the idea that thickness, which again is usually a negative term, it's usually indicative of a lack of material organization, lack of efficiency. Here is it kind of exploited for its peculiar spatial qualities, while the excess of the agricultural residue, it sequesters a significant amount of carbon. There's 229,000 kilograms of CO2 equivalent stored within this building. So the exhibition, as Eric mentioned, is really, we were only able to fit 4 of the houses. The fifth house, which I actually didn't even present, rounds out all 5 houses. It's really those 4 houses on the wall. The exhibition itself is a series of stands, each holding one of the cross-section perspectives open. It unfolds through the space of the gallery. So it's basically the book unfolding left to right around the gallery. We included images, the photographs of the houses above the stand. So those were augments that were added to the original manual section display. And more importantly, we opened up the inside of this. And inside the kind of figure of the stands is a series of displays, each holding a material. And these are organized from most carbon sequestering to most carbon emitting. Not surprisingly, moving from plant-based materials all the way to metals. All right. So this is, I've never presented this. This is work we've done this summer. This will be the last thing I present. And this is very much in progress. So this is not a conclusion, but our question is, in our obsession with straw as a building material, can we get this holy grail of load-bearing insulation? Can we do that? And how might we get to that point? So one way to do it is to work with these gigantic bales. And they present a very different way to think about the tectonics of a building, which we find really interesting. So not only are they thick, as in the 2 or 3 past projects I showed, but they're also strangely round. And so you start to think about these things as a kind of colonnade, hypostyle hall, and they're also really cheap. So at $60 a bale, this is roughly a 5,000, 6,000 square foot space, 75 by 75, and it's $1.75 per square foot because of the inexpensive nature of the material. That's pretty impressive. So you got your structure and your insulation, not including your roof. The roof is another, yes, I know. So, but the walls alone have it. But more importantly, you can get into some really interesting questions about how you might make space. How do you organize this, just even on one level, right? What are the options for carving and thinking about organizing the relationship between rooms in a way that's, I think, fundamentally different than any other material that is out there, right? And of course, it gets even more interesting when you start looking at different combinations of thicknesses and column grids and wall lines and how these things might aggregate in different ways. We also became interested in, if you start to kind of stack them up, could you end up with because there's an excess of structure here, are there ways that we can end up with a very different way of thinking? And this is just a diagram using CLT planks, but some interesting possibilities that could come from this. So the assumption is that you would still need to clad these things, CLT ring beam and bottom plate. You'd use a membrane, a weatherproof membrane, battens, and then a rain screen around the top of it. So one of these things we started looking at is, could we take an existing project that we've built, and this was early childhood education, all had to be single-story because of the nature of the school and the small children. This was a school we did about $180 a square foot in Arkansas, where the relationship between the playgrounds was crucial to the nature of the classroom. So each classroom had this space between the classroom and the playgrounds where you could go outside. The classrooms had all kinds of light and air in them, and we had this kind of central space where this whole thing came together. The downsides of this project, it was steel, concrete, lots of drywall. All of this was trying to figure out how we could turn drywall into something that didn't look like drywall, but it's still drywall, right? So the question we asked is, what if we rethought this project using two different types of straw bales? So this is the jumbo straw bale version, where we not only kind of imagined that we could start to envelop or frame a room with jumbo bales, but use those as the structural point, as a column for a series of reciprocal, a reciprocal frame roof structure with LVLs that would then form a skylight and provide an ability to go from inside to outside in the same way in which we'd already done, but with these jumbo bales. We also like the idea that we could prefabricate CLT bathrooms and position those between two different classrooms and aggregate these classrooms into a pair so that they would share a collective space outside and still have the pair of classrooms. So this just gives you a sense of how this might develop as a whole project. We also said, okay, the problem with that is it's going to be a little more expensive. There's no way you can do a round. It's just going to involve more expense. Could we do a more straightforward rectangular jumbo bale project and still get some of the similar qualities? So you still work with the load-bearing insulative walls that move from inside to outside, simple LVL beams infilled with straw spanning across them. They would have the CLT bathrooms lodged between two classrooms, but also have a collective circulation space in between, so you can move down the hallway, feeding to pairs or mirrored pairs of rooms on either side of this collective hallway. Very simple construction, using transparency where necessary to get light in, but trying to find a way to change the basic diagram of the school we did already through the role of materials, and in particular the role of straw as a spatial and structurally organizing material. So this then leads to the argument saying, okay, we need to find a way that we can, or is it possible that we could compress straw, make it structurally load-bearing, and have it be insulative and not be dependent upon what you get from a baling system that's really not meant for construction. It's meant for just the efficient packaging of the straw off the fields. Could we compress our own and try to find a way to bind straw into a monolithic load-bearing insulative material? Most of the way in which straw is used when it's not done in bales is inserted into a 2x4 frame system. So here, whether it's EcoCocon, where you get the double stud of wood studs that are largely playing the structural role, and the straw is essentially there as insulation. This, of course, allows you to work straw into the existing code systems, so it makes a lot of sense why this is the model. And you can find this in lots of places in the world. And there's even a fascinating company in Maine called Croft that I encourage you all to look at, that at a kind of ground up level is making houses with these prefabricated double stud straw compressed walls. But our question is, could we actually get rid of the wood, not have a wood frame system, but just do a straw-based system? So that meant we had to kind of make a straw compression machine. And this thing uses 2 truck winches to produce about 24,000 pounds of force that allows us to try to at least make prototypical blocks that can get a level of straw. And so we've kind of enjoyed the act of seeing if we could kind of prototype different forms of compression. The issue is largely that once you do this, you have to then hold that compression. It pushes back. Straw is maniacal. The amount of force necessary to keep it into position, you then have to resist that. So it raises the question of, all right, well, what's the binder you're going to use for doing this? So we've worked through, obviously this is wood glue, which turned out to be a disaster. One, it's not great anyways because it's basically plastic, but it also formed a shell around the perimeter of the straw and the inside didn't dry, which of course meant over time it just basically exploded and opened up, right? So not good. Yeah, mycelium, we tried mycelium, disaster, did not work. Same thing, basically mycelium would only grow in the first inch and it's so compressed that no oxygen gets to the middle, would not grow in the middle. The thing kind of slowly exfoliated, and frankly, it rotted in the middle, smelled horrible. We're done with the mycelium in combination with straw if we're trying to use it structurally. We tried making our own soy-based binder. We got a 50-pound bag of soy flour, tried cooking some of our own. Not good, so if anybody has a good recipe for it and can link me to the chemical preservative company that will make this, it's not working. Anyways, we did have some success, but it involved about a month of drying time, which is interesting. So, and then we had to change these test blocks. And again, the goal isn't to make blocks. The goal is to make monolithic walls or monolithic substances. But for these test blocks, we had to find a way to let them air dry. This is a couple of weeks ago. And then finally, once we knew that they were dry enough all the way through, we had these moisture readers, probes, so we could verify that they were, that moisture levels had gone down on the inside. We could release them. And we ended up realizing, yeah, this is starting to work fairly well. So we end up getting a combination of different binders, the working earth, different versions of lime. Cement, of course, work very well. Things that have chemical reactions, the downside is they have a higher carbon footprint. But these worked out fairly well. So the next question is, all right, we've got to test these things structurally, and we have to test them thermally. So these are other views, the mycelium. Oh, I forgot to mention the other thing so these are just the recording of the different experiments. But we also just said, all right, what happens if we work with just a SIP system? Just 2 layers of straw board or plywood, not a wood frame system, but really just enough to hold the straw in position, assuming the straw is going to be the load bearing, but this keeps it in place. So here we were able to get about 163 kilograms of straw per meter cubed, which is really dense. You need about 120 to get to load bearing. So we can easily exceed that, and of course the more straw you pack in here, the more insulation you get. So, and it led to some fun giving straw haircuts, which of course is anyways. So it's just nice to see things in process. See if I can get that to play. I mean, when you start working with chainsaws, I think that's when things get. It's not tailoring what you're. It's a different kind of tailoring, right? So, anyways, so the other thing is we then had to take our blocks and cut them into smaller pieces so we could put them on the Instron compression system. This is a sped up compression test that was done with this straw. Oops, let me get this to work. Well, what's fascinating here is it doesn't expand out horizontally at all, and then it bounces back. And basically the Instron would work until it hit the safety factor and then stop. So this maxed out the machine's capacity to compress. It was about 6,000 pounds. And almost all of the samples had very similar curves. The more you loaded it up, the more it was able to handle and the less it deflected. The problem is it deflects a lot at the beginning. So our issue now is we've got to find a way to get that initial compression out so it can be more stable. Because structural engineers don't really like creep in their buildings, and so that's one of the anxieties that we're working through. So the other thing is trying to figure out how do these things work thermally, because the more you compress, the stronger it gets, but probably the worse it is thermally. So here we set up the equivalent of our easy bake oven with a light bulb in the middle, heating up the inside, and then we were able to place the straw blocks around the periphery, stuck temperature probes into them to figure out how slowly or how quickly heat moved through the thermal mass. But this wasn't getting us to the R value, obviously. We then invested in this R value heat flux sensor, which turns out to not adhere very well to straw, as you can imagine, even with the thermal paste, and we're getting numbers that are all over the place. So unfortunately, I'm going to end the talk on the unfortunate nature of a heat flux reader, but our goal is really to try to get enough data to then know what binder, what density, what hits the sweet spot structurally and thermally to make this thing work. But just stepping back a little bit, I mean, I think that what we're excited by is really seeing this as an opportunity to really rethink what architects' engagement with the built environment is. To not just kind of be in the role of form and organization, but to take seriously the material, not just be specifiers of products that already exist, but we have to push on the very nature of what we're building with and how that's going to happen. There's a lot of work to be done, so because we don't have a lot of time left, but there's a possibility of, in a sense, having a fundamentally different architecture, a fundamentally different relationship between architecture and the built environment, where the consequences of what we build are hopefully beneficial as opposed to as negative as they've been. Thank you very much. Sure.
So we're all going to head to the gallery shortly, but we have time for a couple questions.
Yeah.
Easy one. The fire resistance of straw, right? Have you all been testing that in your work? Also, kind of that as you become more successful, increasing the density.
Yeah. Short answer to that is that once you, it's like mass timber, once you compress it dense enough, it chars, it doesn't burn. Croft has done a number of experiments, Eco Cocoon, all of these companies, because that's the first anxiety, is it's going to burn, right? But it chars. Once it's dense enough, that's why compacting it in the wall, not just loose fill, is really key. But there are a number of videos online of straw burning, and it doesn't burn. Now, XPS, EPS, any styrofoam is going to go up like instantly. So the comparison is actually one of the benefits to straw as an insulative material because it's so much better fire right. And even if it does burn a little bit, it's not as toxic as what comes off of the conventional insulations.
Sure. Thank you. And thank you, by the way. Wonderful presentation. Really interesting projects. You said at the beginning one of the major issues that the industry that we're all facing is the demand for surface area, right, moving forward, and just simply the lack of materials available with regards to the safety of the environment to meet that. Do you feel in your work and your research that biogenic materials have both the longevity to sustain in their use, to sustain buildings that are trying to meet that demand? And do you also feel that the availability of biogenic materials is prominent enough in different locales to meet that need as well? And
Yeah.
another way of asking that question, has your work looked at biogenic materials by climate, right, and identified equivalents by climate as well?
It's a really good question, and one of the simple answer is no. There's not enough high-performing biogenic materials. There's plants have been used for all of human history to make buildings, but in some ways, 20th century modernism and industrial revolution leading up to it was all about getting rid of that, right? So I think one of the questions is, what are the ways to build with these materials that are not simply about returning to conventional ways of using them, but actually invent a more kind of high-performing model of what they are. And there are not enough models of those out there. So, I mean, there are some companies that are, Hemp Texture is making a hemp-based insulation. There's definitely ones that are out there. There's more in other parts of the world than in the States right now. Timber HP is coming out with a wood fiber, has just come out with a wood fiber, and they have a very large plant, relatively speaking, but it's only going to supply a small fraction of the construction industry, right? So the answer is right now, no way. There's not enough materials available. There's not enough demand. People are not working on it. On the other hand, if we're supposed to somehow reduce our carbon footprint and we're still going to stay in the world of architecture and we're trying to get that down 65% by 2030, you're not going to do it by somehow making slightly better versions of steel or slightly better versions of concrete. There has to be a fundamental, radical shift. And the problem is, how do we get there, right? So the answer is right now, no, but the hope is that there's a possibility, but it's going to involve, and I think from the standpoint of architecture and design, not only do we have to look for what's out there, but also potentially invent different ways that we can make these work. There's so many hurdles that, yeah.
The last one for like you mentioned early on in your presentation that a lot of the houses you studied are 1,000 square feet or smaller, and that was in part due to a critique of the residential space. Could you talk more about what it is you're critiquing about the residential space? Is it
at that level, it's just simply excess, right? Yeah. I mean, the general assumption is a bigger house is better than a smaller house, but it's reached the point where our houses are too big, right? I mean, I don't, it's not to say that a big house isn't nice, but there's a level at which we can't keep inhabiting houses at this scale. So,
my thought would have been, is there an idea about the house not as a, one-tier residential space, but moving more towards a multi-generational
yeah.
space?
Well, that, and again, I think one of our own critiques of the book is that we really did just, in order to provide a kind of taxonomy and a consistency, we said, okay, we're not going to do housing. There's a couple of housing projects in there, but they're mostly aggregations of individual units. But no, and I will willingly say that the house is not the future of the collective housing. Different models of housing is where we have to go. That was one of the Achilles heels of the book, that we had to draw what existed, and we couldn't find enough examples of housing projects made with, well, in fact, we find very few, right? So, yeah. Yeah.
Thanks for coming. Great shoes.
Thanks.
Love those. I'm curious. So with these like super dense straw load bearing walls, where do you put them in electrical?
Yeah.
Outside of that?
No, it's a good question, and there's different ways to channel. Again, because it's an extra thick wall, there are ways to channel it in. We were looking with the jumbo bales where they came together, and you have to, Rhino makes them look like they're perfectly adjacent, but they're actually going to be compressed and pushed up against each other to get that, 10, 15 inches of continuity. But that space is available within, outside of it, within the batten system that you have to do to get the rain screen on. And on the inside, even if you're doing an interior finish, you're going to still have that space. So just by way of a specific example, Croft, when they make their panel system, they often run it, they'll run some of the infrastructure within the cavity of the batten, but they'll also channel it, make it available pre-drill for penetrations, et cetera. So, but yeah, I mean, one of the things is because and again, look, one of the downsides of thickness is it's not great for urban spaces where space is a premium, right? So we're talking about a kind of where the thickness of the wall being super thin is not really it's not going to be a big burden on the expense of construction because you have enough room to work around it. But so we're largely talking about environments that are not apartment complexes where things are really tight to each other. Like the fabric of New York is not a great site for straw and those kind of thick walls. So yeah, I just wanted to acknowledge this is not the solution to everything. And they're tactical solutions that would have to be played out in different locations. So yeah.
So of all the materials that you're showing here, which one do you think would hold up the best in cold climates? Kind of back to the previous question about climate. In terms of like extreme freezing and thawing, a lot of these materials and a lot of the houses shown in your book, and I'd like to say I think the book is awesome. Your work is
Yeah.
So a lot of these materials could not be used in a climate that is extremely cold. It seemed like you answered some of these questions with straw, but just wanted to get your quick thoughts.
Yeah, it's a good question. I think that I would we haven't obsessively mapped different climate regions per every material. It's not something that we've done. I will say that one of the things you can do is go through the book and just see which ones are in the northern climate. Not surprisingly, a lot of the wood, CLT, but frankly, as long as you're able to position a fair amount of insulation with a weatherproof barrier, I mean, I think the bigger concern is high humidity, where you're dealing with the inability to dry out, and mold. I think actually cold is not as big a problem as as having excess moisture. And how do you, that also leads to other questions about what are the membranes you're using, and how do you keep everything vapor permeable, which is also not something that we tend to do when we're designing. So it's a large, I don't think it's a one-to-one correspondence. I think it has more to do with how do you deploy the system and what are the things you're trying to attend to. I don't think cold climate presents an excessively complex assembly that say a hot humid. I think a hot humid is actually harder. And some of the examples that are in the hot humid just don't have air conditioning. They let natural ventilation, so as a result, they're not concerned with the sealed envelope. But anyways. Yeah.
So this might not be actually a simple question, but I want to shift for a moment to the kind of disciplinary side of this. I think the technical aspects of this are fascinating. The book lays them out really well. And when I look at that section in particular, the house on the screen, there's a kind of Minecraftiness to the section, right? That you're sort of reintroducing dull mass and subtractive definition of spaces, which is operating kind of exactly counter to the trajectory of modernism, right? And we think of the climate crisis as primarily a product of modernism. And the Marxist, that old Marxist adage, all that is solid melts into air, that was fed through architecture in buildings becoming thinner and thinner and lighter and lighter. And so somehow the antithesis of that project is like a Bucky Fuller dome. Right? It's made of aluminum, it's as thin as possible, it's as light as possible. And it's pitched as the answer to the problems that we have, make it as light as we can. And what we didn't realize until it was too late is that its carbon footprint was massive.
Right.
And so there are these interesting reversals that you see in the way that the architecture plays out. That modernism kind of drove thin, had this kind of invisible shadow of massive impact. And the work that you're pursuing seems to get thicker, more cellular, more kind of individualized in its kind of spatial conditions, and yet has a sort of more mass equals smaller footprint. And so I wonder if you could just riff for a second or two on the value of those kind of counterintuitive intellectual leaps that seem so central to the way that you and Paul and David work. Because I think there's something really instructive about how to get out from under some of the habits that some of the modern habits that have become so ingrained in the way we think. And by doing things the wrong way on purpose, you actually open up new kinds of frightens.
Yeah. No, I think that's really well said. And you certainly, lingering in here is an implicit critique of the absence of material consequences in Rhino. There's the absence of material consequences when the sole interest is the form and the surface. There's a critique of, as you said, modernism's attempt to make thin and lightweight. How heavy is your building, and the lighter the better. That all of those assumptions that frankly many of us inherited as truths, right? Thinner is going to be better than heavier. Less material is better than more material. And at a certain degree also, there's a level at which we as architects have found ways to ignore everything that exists within the wall, as long as we can get the two surfaces to do something we appreciate, right? I think all of those things are in here. And I know that these things are purposely excessively thick. I mean, there's a rhetorical value to what we're trying to do here. So, and that, I mean, look, we have animals burrowing in. I mean, there is an attempt to say, but it also comes down to, there's so many other things that are associated with it. The assumption that you don't have to maintain a building, which we know there is no building that doesn't need maintenance, but the assumption is somehow you can buy a product that's maintenance free. And that then leads to an incredible amount of plastics, and now we value plastics because it doesn't have to be maintained, right? There's the assumption things don't age, I can go on, and these all come from the same source material. And we're kind of questioning, and actually we effectively have to question all of the tenets of modernism, because where we're going with modernism, parts of it are amazing, but parts of it are really damaging, and we need to figure out what are the other ways to move forward. We can't just do less bad and continue, and that's the other issue, is that if what gets us excited is the opportunity of doing something new, that's always been the interest, right? What are there different ways of operating, and can it be logical, can it have a rationality, can it be ethical? And there's a nice way in which this is starting to congeal that gets us very excited. It's a terrible way to run a business, so that's another story, but nothing like going into a client presentation and say you're only gonna work with plant-based materials to make sure you don't get the job, so. Anyways, I think you're absolutely right, like that, in there is a lot of critique, but also a hope that one doesn't just say, we can't build, architects are horrible, we shouldn't do anything, we should get out of the practice, everything that's built is all we should ever build, that's it, and that world of negation is absolutely out there. So, and it's gonna come back even harder and harder, right? So unless there's a way forward that has optimism and some degree of design having an agency, why are we here, right? So, sorry that, that got a little preachy, yeah, so. Right.
Look how bad this is, and then it either says, don't do it, or more research is needed.
Right.
And what you offer is, however halting and requiring further.
More research is needed.